Question number 5. So here we have an array of integers where we need to find one magic index, which is the element, and the particular index is equal to the index value itself. So here we can use binary search approach, which is much more efficient than the native approach. So how it works? So for example, we have an array of these numbers, and we have to find the index, the magic index. It means that the element and the particular index is equal to the index itself. So here we have following elements and the following index values of these elements in the array. So we see that just this particular element is equal to the value of index itself, so we have to find this index. And it says in the problem that there is just one magic index in the array. And here we can use binary search. Binary search means that we always can divide our search number of elements. So for example, we have here 8 elements in the array. We'll divide it by 2, which will make it 4, and we will check if the fourth element is equal to the index value. And once we see that it's not equal, we will just compare which we just need to decide which half of the remaining array we need to continue to search for our magic index value. So here we see that 4 is less than the element in the array itself, so we can say that the number that we're looking for is in that half. Here we have 4 elements, we divide it by 2, and see if the element at the second array is equal to the index value. We see that it's not equal, and we see also that the value in the value of index is less, the element is less than the index value itself. So from here we can say that we need to search at this half, and again we will just divide it by 2 and look to this half of the subarray, and again we will just 2 divided by 2 will make it 1, and at array 3 we will find that element is equal to 3 itself. So in function it will look like this. So our function will return integer, the passing argument will be an array. So here for binary search we will need to define the lower pointer, which will be the 0, and define the highest pointer, which will be the last element of an array. And we will run our while loop, until our low pointer is less or equal to our highest pointer. And from here also we will need to define our index value, which will be like something like divider of an array. It will keep dividing our array and like making it smaller, and will guarantee that our searching function will be working better. So here we'll always subtract our high variable by low variable divided by 2 plus low. It will always give us exactly the middle point of our searching area. So, and here we will say that if our element at the particular index is equal to the index value itself, we'll just return index value. If it's not, we will see, we look at that if our element at particular index is greater than index value itself, then we will just change our variable high by subtracting from index value by 1. So we will just, for example, here we're looking for 3, and at the first phase we see that our element is greater than the index itself. So so from here we are sure that our element that we're looking for is at that half. So we're just changing our high variable and making it the last element of our subarray. So here it will be 3, so 4 minus 1 will make 3. If we see that the element is less than the index value, we are sure that we need to search our magic index at another half. So in that case we're just changing our low variable and incrementing our index value by 1. So if we're not able to find our magic index in the array, it will mean that there is no such magic index in our array. In that case we're just returning -1, meaning that there is no such thing such as a magic index. Since we're using binary search, the time complexity of binary search is log n, meaning that, for example, here in that array we have 8 elements. It means that log to 8, it means that we basically need to find element in the an array of 8 size within 3 attempts. So in 3 attempts we are able to find the element that we are looking for. that we are looking. So time complexity is O log n, and the space complexity O constant, because we are using existing array and we are not we're using the constant memory. And follow-up questions say that follow-up question for this problem says that if there are not distinct elements in the array, the values in the array, meaning that the values in the array are not distinct. So in that case, we will use just a naive approach. Looking to all elements in the array. And print all elements that are where the index value is equal to the element at that particular index in the array. And the time complexity of this approach will be O(n), because the number of operations will be equal to the number of elements in the array.